We are going to find areas of curves under the x-axis. Look at the description. In the examples so far, which are these examples? Each time we were calculating the area for the colored region, which was between the curve and the x-axis, with the condition that the curve is above. Notice here the curve is above in both graphs. The area that you were calculating was above the x-axis. If the area between a curve and the x-axis lies below the x-axis, so here we are taking another sample, where the area is below the x-axis while being between the curve and the x-axis. Then integral y dx, which is the rule that we were using to find the area, will give a negative answer. So how do we solve this type of question? This is what we will know in this example. Find the area of the finite region bounded by the curve y equals x into x minus 3 and the x-axis. Look at this curve. If we expand this curve, then it will be x squared minus 3x. That means this is a quadratic equation which is represented by a parabola. Since the coefficient of the x squared is positive, then the parabola is opened upward. In order to do a proper sketch and to see whether this area is above or below the x-axis, we need to calculate the x-axis intercepts. For the x-axis intercept, we set y is equal to 0. So, x into x minus 3 equals to 0. That means either x equals 0 or x minus 3 equals to 0, which is x equals to 3. These are the 2 points. Therefore, the points are x0, y0. The second one is x3, y0. Look at the coordinate plane. We draw 2 axes, the x-axis and the y-axis. Now we need to assign the points. The first point is 0, 0, which is the origin. The second point is 3, 0, so it is here. We will draw the parabola in a way where it is opened upward. This is how it will look like. Pay attention that we want the finite region. Of course, we won't take these because the curve is continuing here. So the limited region between the curve and the x-axis is here. This is the region, and as you can see, it is below the x-axis. In order to solve the area, we used to write integral of y dx, where the y is the equation here. So it is x into x minus 3. Now we take the values of x where it started and ended. It started at 0 and ended at 3. Then we do the normal integration. We write 0 to 3 here. For the y function, we will not take the factorized form. We take the expanded form. So x squared minus 3x dx. Now we integrate. X squared will become x to the power 3 over 3 minus 3 x to the power 1. 1 plus 1 is 2, so x squared over 2, starting from 0 and ending at 3. Now we substitute the values. 3 to the power 3 over 3 minus 3 times 3 squared over 2. Minus, now for the lower limit we have 0. For the 2 parts, x equals to 0, so the value here is 0. Now let's calculate the first part. 3 to the power 3 is 27 over 3 minus 3 times 3 squared is 27, so 27 over 2 minus 0. As you can see, the 27 is repeated, so we put it outside. That means 27, what remains is 1 over 3 minus 1 over 2. So 27, inside the parentheses we take a common denominator, which is 6, because here we multiply by 2 and here we multiply by 3. So 2 minus 3. 27 multiplied by minus 1 over 6. So minus 27 over 6, if we simplify, then it is minus 9 over 2. Or in decimal form, it is minus 4.5. This is the answer for the definite integration. However, because it is negative, we cannot say that this is the area. In order to calculate the area, we take the positive value of this answer. So, the area of the curve is the positive value of this, which is 4.5. Therefore, we can say that if the area of the curve is below the x-axis, then the area is not integral to y dx. Instead, it is minus the answer of the integral y dx, so that the final answer of the area would be positive. Look at the description in the book. First, we sketch the curve. It is U-shaped, so parabola, and it crosses the x-axis at 0 and 3. The limits on the integral will therefore be 0 and 3. And we do the calculations and we integrate as usual. Finally, state the area as a positive quantity. So the answer was 4.5.